Very good. So hello, everyone. And before I start, I would like to thank Martin for inviting me to give my first partly in-person talk since 2019. So before I start, I would like to give you a small plan for my presentation. So in the first part, I'll try and give you some motivation for the definition of classical divided power algebras and translate some of the results on those into a somewhat more modern language. Then I know that you had a full term recently on operads, so that's very practical for me because I will be using a lot of operads, and I'll try to define the notion of divided power algebra over an operad, but the definition will not give a practical characterization of those objects. So we're going to search for a characterization of those divided power algebras. And the problem is that this characterization will be completely general, and so it will come out as very complex and hard to use. So we will need to refine this characterization into each case where we fix the operad or the characteristics of our field. So I'll try to find a minimal characterization in particular examples. All right, so the first example of classical divided power algebra appeared on the classifying spaces of groups and Eilenberg-MacLane spaces. So let me give you some very basic reminders about these objects. If you have a group G, what we call a classifying space is a topological space BG such that the fundamental group of BG is equal to your group G and all other homotopy groups are trivial. Now, there is always a classifying space. In fact, you can construct many of those, and they're always of the same homotopy type. And there is a natural construction using simplicial set to build these classifying spaces. So since you have a natural way of constructing an object, and this kind of object is always the same up to homotopy, it means that we can create invariants of groups by studying the topological invariant of their classifying spaces. And this will also give a lot of information on the topological invariant that we study. For example, if you take a group, you can study its homology, which is by definition the homology of its classifying space. And this homology has an extra structure because you started with a group, which means that you can define a multiplication on the homology from the multiplication of the group using what we call the Eilenberg-Zilber shuffle map. So let me recall you how this works. You take a homology class X of degree I and a homology class Y of degree J. You take a representative of each, and you want to apply degeneracies to both of those to obtain something of degree I plus J in both cases so that you can multiply them together. What the shuffle map does is to sum all the possible ways of applying those degeneracies indexed by shuffles. And a shuffle is just a partition of the set of I plus J first integers into one set of I element and one set of J element, which you take ordered following the natural order. Now, you can apply those degeneracies following this order, and there's a shift of index just because the degeneracies are indexed from 0, and I'm usually indexing my shuffles from 1. All right, so this multiplication is a bit special, and I would like to describe to you easy examples of this kind of multiplication. Yeah, of course. Sorry, I'm not sure what you mean.
The map from G cross G
into G.
B is like a functor for the groups.
Yeah.
The topological spaces.
Yeah.
Topological groups, topological spaces. So that doesn't have to apply it to like a map of groups.
Well, the thing is, you have a map from G times G into G, which is a set map. And that's this set map that you apply B to and you obtain a set map. But then when you look at the chains and then this, using the shuffle map, this will go through homology. What you obtain is indeed a group map. All right. And so if you pick the easiest example you can find, well, let's say that your field is the prime field of characteristic 2 and that G is your Z over 2Z. Then a classifying space for G is given by the real projective space RP infinity. And this, as a vector space, looks a bit like a polynomial algebra over one generator. So as a notation, I'm going to denote by X bracket n the elements that will correspond to the monomial X to the n. But the multiplication that I obtain with my shuffle maps is not the multiplication of polynomial. Instead, when I take an X bracket m and multiply it by an X bracket n, what I obtain is X bracket m plus n multiplied by a binomial coefficient m plus n, choose n. And this algebraic structure, I will denote it by gamma x. So it's the polynomial algebra with this weird multiplication that has a coefficient. As an algebra, it's not isomorphic to the algebra of polynomial because, for example, it's not generated by x. If you multiply x by itself, you get 2x bracket 2, and we're in characteristic 0, so that is equal to 0. But we can give a list of generator, which will be the x bracket 2 to the k. So if I want to give more examples of that type, I can just take that algebraic example and say, okay, now I'm going to build the same thing over any field. So you take your polynomial algebra over one generator, and you define the multiplication x bracket m times n bracket n is equal to this thing with the binomial coefficient. If the characteristic of the field is 0, then this is isomorphic to your polynomial algebra by sending those x bracket n to x to the n divided by n factorial. So morally, in our head, we have to think of those x bracket n as playing like x to the n over n factorial, and that justifies the name divided powers. But of course, if the characteristic of the field is positive, dividing by n factorial does not really make sense. So instead, we have to kind of list the property that those bracket n satisfy. So what I'll do is I'll define gamma n of x as being x bracket n to give you the impression that I have an operation gamma n that sends x to x bracket n that kind of does this divided power operation. And now I can give you the real definition for a divided power algebra. So for that, I took a screenshot of the original paper of Cartan from the 50s, where he defines divided power algebras as commutative, associative, unital algebras that have a family of operation gamma n that play the role of the divided powers, which are only defined on a certain augmentation ideal. I don't want to spend too much time on that, and satisfy a bunch of relations. And I'm going to give names to those relations in the next slide. So let me go through those relations with you. There's a first relation that you do not see on the screen, which I call S for symmetry. And in fact, it's represented by the fact that the multiplication itself is commutative. Then you have that first relation H, which is up here, which tells you morally that a divided power of power 0 should be kind of forgotten. It's kind of the units. Then you have a monomiality relation, which here is expressed in terms of degrees, because Cartan is working with graded algebras, but I can state it in a different way using coefficient of my field. So here, if lambda is a coefficient, gamma k of lambda x is lambda to the k gamma k of x. Then you have a relation which I call reduction with respect to the repetition of inputs that say that if you have an expression with twice the same input x, you can reduce it to have only one x. And the price that you pay when you have two divided powers like that, gamma k of x, gamma h of x, is to multiply by a binomial coefficient. So that's exactly the definition of the multiplication that I gave before. You also have a relation between divided powers and sum. So Martin was telling me that it looked like a Cartan formula, but of course, Cartan does not call it a Cartan formula. He calls it a Leibniz formula. So the name Leibniz formula stuck for that. It's like a Newton's binomial coefficient formula, but there's no binomial coefficient. And then you have a unitality that tells you that one of the operation has to be the identity of your algebra, and a relation that tells you how divided powers react to the product and how divided powers react to divided powers. Of course, if you try to make the computation of that in characteristic 0 by taking the divided powers gamma k, it sends x to the k over k factorial, all those relations are satisfied. But even in positive characteristic, it makes sense to define algebras that have this list of operations. All right, so I defined the divided power algebras, and there was some study on it. So we have a couple of results. The first one is that if you have a vector space V, you can define the free divided power algebra gamma V generated by V. And this is given somewhat in the same way as a symmetric algebra. So it's a sum of tensor power of V, but instead of modding out by the action of the symmetric group, which permutes the factors, you will take the submodule of invariant under this action. Now, because I call that the free divided power algebra, I'm supposed to define the multiplication and divided powers on it. So first, the multiplication. If you take a tensor of length n, which I called V, and a tensor of length m, which I call W, and you suppose that those are invariant under the action of the symmetric group sigma n and sigma m, then when you tensor them together, you get a tensor of length m plus m, which is invariant under the action of sigma n times sigma m. Now, you can consider sigma n times sigma m as being a subgroup of sigma n plus m, the Young subgroup. And to obtain something which is invariant with respect to the whole group, you're just going to sum over this quotient to obtain the invariance that you need. Now, one set of representative for this quotient is the set of nm shuffles. So we call that product the shuffle product. And then if you need to create divided powers for this product, it turns out that the tensor power n time is a good candidate for a divided power. So if I take the free divided power generated by one element, I get exactly that gamma x that I was talking about earlier, these polynomials with the binomial coefficient. And you might be wondering why I even care about those algebras. And the original excuse was those Eilenberg-MacLane spaces. But more generally, Cartan has shown that if you start with a simplicial commutative associative algebra and look at its homotopy, using the shuffle map, you obtain a commutative associative algebra. It turns out that it always has divided powers. So that means that this appears in nature. All right, and for example, that was the case for classifying space, and that's why we obtained in the end a divided power algebra structure if the group we started with was abelian. All right, so these are the classical results, but I can reformulate them in a somewhat more modern form. Well, I'm going to redefine this gamma v this time by being the sum for n strictly positive, and the reason for that is that I want to work on non-unital algebras because you can add the unit artificially afterwards, but it causes a lot of problems if you keep your unit all the time. You have to have those augmentation all the time. So from now on, I'm working on non-unital algebra. And this association, gamma of v is equal to that sum of invariant space, has what we call a monad structure, which means that it has a monoidal structure for the in the category of functors with composition. So I can define this monoidal structure. First, if you take a vector space V, then gamma V will be spanned by what we call divided power monomials, which are those elements of the form T. And they are products of divided powers of elements in V, where, of course, what I denoted by divided powers is the tensor power, and the product here is the shuffle product I was showing earlier. So this offers a span of gamma V. So to give a unit from V to gamma V, I'm just going to send every functors of V to gamma 1 of itself. And now to create a composition, what I need is to take divided power monomials of divided power polynomials. So imagine that in this big expression, all the T1s to Ts primes are themselves divided power polynomials, so sums of things of that type. And well, you have a product of divided powers of sums of product of divided powers, but this satisfies some relation that I showed you earlier, which are, yeah. This thing is sigma n invariant, yeah. Yeah, that's why it's like, this is repeating V1 R1 time, and then you take shuffle products, so it will be invariant. And so if here you have a divided power of a sum of products of divided power, using the Leibniz formula, the monoidal formula, the composition formula, you will be able to rewrite it as a long divided power monomial. So that gives you expressly a composition for this monad whose algebras are divided powers. And so the result of Cartan can be reformulated by saying that you have that homotopy functor that takes simplicial commutative associative algebras and spits out a commutative associative algebra. These factors through the category of divided power algebras. Anyway, that's just categorical abstract nonsense. But now I would like to give you maybe another flavor of those divided power algebras that have to do with Lie algebras. So recall that a Lie algebra is a vector space with a binomial, bilinear operation that we call the bracket, which is anti-commutative and satisfies that Jacobi relation. Well, in characteristic P, there is a notion of what we call P-restricted Lie algebra or just restricted Lie algebra, which are those Lie algebra that have an extra operation that we call the P-map, which is denoted with this tantalizing bracket P, and satisfies three relations. One is like the monoidal relation. The other one I call Leibniz relation because it tells you what to do with the sum, and composition tells you what to do when you have a bracket of a P-map. Now, there's some Lie polynomials that appear here. You just need to know that there's an expression for that in the literature, but it's kind of complicated to define. And those P-restricted Lie algebra, I'm going to try and convince you that this is the right notion of Lie algebra when you are over a field of characteristic P. So to do that, I'm just going to shower you with examples which look a lot like what we do usually when we want to obtain a Lie algebra. So you are over a field of characteristic P, and you have an associative algebra. Then you can make it into a Lie algebra by just taking the anti-commutator. Turns out that this is a restricted Lie algebra where the P-map is given just by the P power. All right, so that may be not very convincing because an associative algebra is stronger than that, but there's a couple other examples. If you take the derivations of a non-necessarily associative algebra, we know that this is a Lie algebra already, but we can define again a P-map by the P-th power. And now one example that in my head motivates even more this example, even if I'm motivates my point, even if I'm less of an expert on that. If you have an algebraic group over a field of characteristic P, Borel has proven in '91 that you can define a P-map on the Lie algebra associated with it. And so this, in my mind, sounds like, yeah, restricted Lie algebra is perhaps the right notion of Lie algebra in characteristic P, or at least it's a natural way to think about Lie algebras in characteristic P. And the fourth example that I put here is, in fact, relating with divided powers, because if you have a simplicial Lie algebra, its homotopy is a Lie algebra, and it has a P-map. So perhaps restricted Lie algebras are to Lie algebras as divided power algebra are to commutative associative algebras. So to make that a bit formal, I need a theory that englobes commutative algebras and Lie algebras, and that's when operands come into play. So I'm going to redefine operands for you, and you have to keep in mind that the point of an operand is to encode operations. So the first, maybe naive definition is to say, well, an operand P is a sequence Pn for integer n, where Pn is a vector space that contains elements that we call operation of arity n. And we like to think of them as really operations. So we draw them as these corollas, where here mu would be the name of our operation, the name of the element in Pn. And we would label the leaves from 1 to n to say, I can enter n things and comes out as one thing, applying mu. Now, what do we like to do with operation? First, we like to be able to permute the inputs. So in here, we are going to look at actions of the symmetric group over the vector space of operation of arity n. And we like to compose them. So for example, if I take my mu that has arity n, and I take n operation nu1 to nu n, I'd like to be able, every time that I draw this big grafting tree here, to spit out an operation that has for arity, well, the arity of nu1 plus, etc., plus the arity of nu n. And all of these data, we would like it to have a unit for composition, which is given by an operation of arity 1, with a relation of associativity for this composition and a certain equivariance with respect to the action of the symmetric group. So that's perhaps the naive or the classical definition of operads, but there is a more categorical definition, which is quite important in my case. So I'll go over it for a while. We first define the category of symmetric sequences, which are the categories of lists, mn for all integer n of sigma n representation, with the morphism being a list of equivariant maps. And first, we define a tensor product over those symmetric sequences. Yeah. Yeah, because of the nature of divided powers, I'm really in algebraic cases. So I always have vector spaces or modules over a ring, but I prefer staying in vector spaces. Exactly, that's it. And so the tensor product looks like the graded tensor product, with that catch that if you take m, the arity I elements in M and the arity J elements in N, and you tensor them together, you only have an action of sigma I times sigma J on them. So to create an action of sigma I plus J, what you do is you induce. So that's for the tensor product. And we define another product, which we call the composition product, whose definition is slightly harder. So let's go over it. If you take the arity n element of the composition product of M by N, it's the same as the sum for all k positive of arity k operations in M. And then you have to think that you're composing operation of arity k with k operation in N. So to do that, we tensor over the symmetric group with the arity n operation in the tensor power k time of n. Here, the action of sigma k is given by, on one side, on mk, well, it's given the definition, and here it's by permutation of the factors. Yeah.
Correct. Your symmetric sequences start with index of 0.
Yes.
And they're integers.
Exactly. Yeah. Yeah. There's definitions without the integer 0, but I'm using the 0 still because all the articles that I used had the 0. Anyway, the categorical definition of an operad is that of a monoid for this particular composition product. Now, when I say that operads encode operations, on what does it encode operation? Well, if you have an operad, you'd like to have algebras over this operad. So again, you have kind of an intuitive definition and a categorical definition. So let me give you both. You have to think that if you have an operad P, you'd like the P-algebras to be those vector space that have all the operations that are encoded into P. Yeah. Sorry? Yeah, P circle P into P, and you have a unit as well. So you have a map from a certain unit that I didn't present here, which is in arity 1 into P. So that will give you the unit for that composition product. Yes. And so you have an operad of associative algebra, which is denoted by as here, an operad of commutative associative algebra denoted com, an operad for the Lie algebras. And one easy example of operad is that of associative and commutative algebras, because it's just given by trivial representation everywhere. Here I wrote only for n greater than 0 because I'm not considering units. So my zeroary module is 0, but you can also consider the unital version of that. And all the structure maps are isomorphisms. Now, more precisely, if you want to define algebras, what we do is just like I told you about monads before. Well, you take an operad P and you create a monad in vector space, which sends a vector space V to that bigger vector space SPV, which I can define as being the composition product of that symmetric sequence P with a symmetric sequence, which is V concentrated in arity 0. And by defining that, I can prove that this has a monad structure. And for example, well, for the operad of associative algebra, what I should find is the monad of free associative algebra, which is also called tensor algebra. For commutative associative algebra, you have the symmetric algebra, etc. So by definition, what we call P-algebra is actually an algebra over this monad that we created from the operad. But I'm not here to talk about algebras over an operad. I'm here to talk about divided power algebras over an operad. So now that I defined all of that, I have to give, again, the same definition, but slightly changed. So let's define another composition product on symmetric sequence that we define the same way, except that instead of tensoring over the symmetric group here, we are going to take the submodule of invariant under the action of the symmetric group. And we can again define a functor gamma p this time that will send a vector space V to P circle tilde, which is this new composition product. Sometimes it's called the restricted composition product with that symmetric sequence V concentrated in arity 0. So the funny thing with that is that it's not always a monad structure, but it has a monad structure when the operad P didn't have arity 0 operation. There's a problem with the associativity of this product otherwise. And another remark is that, well, for the operad of commutative associative algebra, our gamma with the composition that I didn't show here is exactly the free divided power monad.
Sorry, Sacha?
Yeah.
In the top displayed equation, you said that you're looking at the diagonal action by sigma k.
Yeah.
And you take the variance.
Yeah, that's it. So it's the diagonal action here on MK and here on the kth tensor power.
Oh, so you're saying that's a monad on vector space.
Yeah.
So P tilde circle B is another vector space.
Exactly.
Does this include or something to the circle one without the tilde?
There is actually a norm map between the two. When you want to go from the co-invariant to the invariant, there's this map that just sums every element in the orbit, and that's called the norm map, and that will give you exactly, and it will give you all the extension restriction of scalars that you can imagine on your monad. So a divided power algebra is in particular an algebra over this operad, but it has to have more. And the question is, what is more? All right, so a natural definition for that, of course, I already used it, is to say that an algebra over this new monad is a divided power algebra. This definition was in the now classic article of Benoît Fraisse from 2000, where he gave that definition and then proved that for the operad P of Lie algebras, divided power algebras were indeed restricted Lie algebras, so justifying my kind of motivation earlier, and also proving a generalization of Cartan's result, saying that if you take the homotopy of a simplicial P-algebra, this thing has divided powers, which is shown by this factorization diagram. Now, the problem is that saying that something is a divided power algebra over P right now is saying that it's an algebra over the monad gamma P, which just gives you a map from P circle tilde A to A if A is your divided power algebra. And that's not a very nice characterization of your objects. You don't know exactly what they are. You know that they are P-algebras with something else, and you don't know what the something else looks like in terms of operation. So that's where my work come in. I'm going to try and characterize those objects.
I'm sorry, Sacha, can you
Yeah.
just go back to the previous slide?
Yeah.
The forgetful functor that forgets to define power operations is always faithful, but rarely full.
Yes, I think that's exactly what you said. If you take two divided, no, wait, it's full, but it's rarely faithful. So you can find all the P-algebras with a divided power algebra, but two divided power algebra can have the same underlying P-algebra.
Right.
I think I got it right, but I could still.
I was just wondering about the hook arrow. What was your
Yeah, I
connection?
think
I mean,
hook
it's
arrow.
certainly not
I think hook arrow is a bad idea from me to have written, because as I said, like it's rather more like a surjection, but like I'm thinking differently about it because it's like P-algebra with something else. But in fact, you're right.
It's a forgetful
It should rather be like a surjection rather than an injection. I agree with that. Yes, the S is for simplicior here.
And so it is faithful, or
It's faithful. No, it's full, but it's not faithful.
that's a different issue.
Yeah, yeah,
It's an object, it's an object, right?
yeah, yeah.
So it's not, it's essentially subjective. Is that what you're saying?
Yes, that's what I'm saying. So yeah, I think my hook here is just a very bad idea.
But no, but it is faithful, right? I mean, if two maps of say divided power algebras have the same underlying map of the algebra,
Yes, then they're the same. You're right. Yeah, you're right.
Down to sets
So yeah, I'm confusing between what happens on the objects and what happens on the morphisms, but you're right.
So it's essentially subjective says something on objects. but
Yeah.
It's faithful is why you write.
Yes, yes.
But it's not
Sorry.
full. It's not full.
Thank you for proving that my notation was not that stupid.
Wait, is it true that it's essentially subjective? Yeah, it's saying that any algebra can be endowed with some. Is there like a trivial?
No, you're right. You're right. What I say is wrong. What I say is wrong. It's not faithful at all, because I can actually prove that, because, for example, if you have an algebra, then you can have x to the power n. But if you have a divided power algebra, this is supposed to be equal to n factorial gamma n of x. So if you have the bad chance that n is greater than your characteristic, this is supposed to be 0.
Oh, right.
So it means
that
that
puts a restriction
you would
on
have
the
x to the power n to be equal to 0. So yeah, what I'm saying, like I've said a lot of wrong things at the moment. All right. So yeah, the hook in fact is not that bad.
The reason it's faithful is because it's just like a map, except it's just a map with an extra restriction.
Yeah, it forgets things. So
Compatible with the gamma structure.
yeah,
Like a map is like,
yeah, the map is a P-algebra map plus it satisfies something. Yeah. So I want to give you a sort of hint of how I build my characterization. So let's remember that, as I said before, so far a divided power algebra over an operator P is just given by an evaluation map FA from gamma PA to A, satisfying some relations. So what I'll do is first define a set of generators for gamma PA, which is not a base, it's just generators given by generalized divided monomials. Here is how I create it. You take S elements inside your vector space A, A1 to AS, and you want to repeat each of them a certain number of times. So you get A1 tensor R1, etc., AS tensor RS. That's a big tensor of length R1 plus RS, which I call this integer n. Now, if you want to bind them together, you need an operation of arity n. And if you suppose that, well, if you look at this tensor first, you can see that it's already invariant under the action of the Young subgroup, sigma R1 times, etc., times sigma RS. So if you suppose that your operation mu of arity n that binds them together is also invariant under this Young subgroup, and you want to build something which is invariant with respect to the whole symmetric group, you need again to sum over a certain quotient which is represented by shuffle. So this, for example, I could replace it by shuffle R1, etc., RS. And it turns out, so the fact that I'm telling you here is that those elements generate the vector space gamma PA. So if I just look at the image of those, well, I know what my map looks like. So what I'm going to do is every time I have a list of integers R1 to RS, which I called R bar, and an operation that has as arity the sum, and which is already stable under the action of the Young subgroup sigma R bar, which is sigma R1 times, etc., sigma RS, I'll create an SRE monomial operation, beta mu R, that takes A1 to AS to the image of this big monomial T under my evaluation map. So I've formally created operations, but first, I don't know if this is a sound definition, if I'm correctly defining an operation, a set map. And second, I don't know what relation those operations satisfy with one another. So the whole bulk of the proof is now saying, well, this is well defined, and here are the relations that it satisfies. So here is the theorem as it stands. A gamma P algebra is the same thing as a vector space A equipped with huge family of operation beta mu R of arity, whatever the length of that partition R is, that satisfy a list of relations, which I have hidden under the rug because they're quite complicated, but I've put them at the end of my slides. So if you want to see them, I can show them later, which look like symmetry, homogeneity, monomiality, reduction with respect to repetition of inputs, Leibniz unitality, and composition, just like in the classical case of divided powers. Now, the good part about this theorem is that now you can say, well, I have a divided powers, so it has those monomial operation that satisfy those relations, and you can actually compute on those. And also, well, in the case of commutative and Lie algebra, we already had those algebras with some monomial operation, far fewer, but it's, again, the same kind of flavor of definition. Vector space with an algebra structure and with monomial operations. But the downside is first that the formulas are super hard to work with. They're very ugly. And there's way too many operations. If you look at just restricted Lie algebra, the definition had a hook and a P map. But with this characterization, you have an infinity of operation that then you have to minimalize by proving that they're related to one another. So that's why this theorem, well, it's the right beginning of study for a divided power. But then depending on the opera that you choose and the characteristic, you have to simplify. Otherwise, working with that is a bit too hard. So now I'm going to try and simplify this with a couple of examples before I finish this talk. So let me show you what kind of characterization I could find. I started first with a toy example of what we call level algebras. That was kind of like the central object of my thesis, so why not try it on that? So a level algebra is a vector space A that has a bilinear commutative but not necessarily associative operation that satisfies a certain kind of interchange law. Here you can see that the B and the C in my product, you can swap them. And because it's commutative, it means that all of those can be swapped. But A star B star C is not the same thing as A star B star C. So you can only swap the things that are enclosed in the same amount of parentheses, pretty much. All right, so as a fact, there is an opera that governs those kind of structures. And if you want an easy example of level algebra, you take your commutative associative algebra, and instead of multiplying A and B, you add a constant in front of that. That will kill the associativity, but you will still have a level algebra. So that's just an easy example of a level algebra. Now, if I apply my theorem, I get a huge characterization for the divided power level algebras, which are level algebras plus many operations. And I can simplify this, but I cannot simplify it in general as much as getting a finite number of operations. The general characterization over any field is infinite and is not nice to work with. However, if I specify the characteristic of my field to be 2, then I can prove that the divided power level algebras in characteristic 2 are just level algebras that have one operation, which is a sort of divided square. But any other characteristic, that wouldn't work. The thing which is very funny is that if you have a presentation of your operad, you cannot derive a presentation of the divided power structure related to your operad. That's what makes things so complicated with those. And so, all right, that's just a toy example, but I can give you more. Yeah.
I'm still absorbing that, for example, of level algebras.
Yeah.
The example there
Yeah.
happens to be associative. Or am I misreading?
No, it's not, because now if you do A star B star C, or maybe it is, wait, maybe I did a mistake again. Let me see. This is lambda AB star C. Yeah, it will have always those. I just chose a bad idea because you have this lambda square every time. So I didn't choose the right one, because if I do on the other side, I also have a lambda squared. It depends on the amount of stars that you have. All right, so that was a wrong idea.
But it's still a level algebra.
It is, but it's not an interesting one because it's associative.
So what would be
Right.
a good example of non-associative algebra?
Well, I can give an example, which is historically the reason why they were defined. If you look at Cartan modules that happen in unstable cohomology, these happen to be level algebras, and even the free level algebras over one generator, if you look at the Cartan module in characteristic 2.
So you take like a universal one, so you just take all symbols put beside each other.
Yeah.
That satisfy that. Modulo that.
Exactly, of course, because I have an operad, I can create the monad, and so I can look at the free level algebra over a certain amount of generators. So it's just that I wanted like an easy example, and this one is just the wrong one to use. All right, so maybe if I plus something that would work. Anyway, I can find a better example later. Let me give you more examples of characterization that I could find after that. So distributive laws is something that gives you an operad structure, a big operad structure from two small operad structures. So the idea is, again, I'm an algebraist. I know how to study divided powers. I would like to know if from a big operad, I can break up the divided power structure into the divided power structure of smaller operads. What a distributive law does is to give you an operad structure on a product of operad. Because if you have two operads P and Q, then there's no reason that P circle Q is an operad as such. It doesn't have a product. To define a product, what you need is, well, you want a map from P circle Q, circle P, circle Q, and go to P circle Q. Well, one thing that you can do is find a map that will swap the two middle things, Q and P, and then apply the product of P on one side and the product of Q on the other side. Now, if you have a map like that, and you want it to give you an operad structure, you need it to satisfy extra conditions to give you associativity and unitality. Well, that's the definition of a distributive law. Any map that swaps those two things and gives you associativity and unitality is called a distributive law. And so, well, at the beginning, there was no reason why, if you have a product of operad P circle Q with a distributive law, the divided powers over this P circle Q had no reason to be connected to the divided powers over P and the divided powers over Q. But in fact, there's an old result of John Beck, who defined pretty much those distributive law, that says that if you have a distributive law between two, if you have a, monad structure on the product of monad, it has to be connected to distributive law. And this pretty much told me that I should be able to find the connection between divided powers over P circle Q and the divided powers over P and divided powers over Q. So let me give you an example. You know the divided powers over P, you know the divided powers over Q, and you're studying kinds of algebras that are governed by a product of those two operads, P circle Q, with a distributive law. Well, if you know both of them, you're almost there. You can almost give the divided power structure over the product, but for that, you need to use a certain distributive law on the divided powers. And what I did in my article is to give an expressively an expression of that distributive law. And again, it's quite complicated to write, so that's why I didn't write it, the actual formula in this paper, but there's a couple of examples that I can show you here that are a bit interesting. All right, so yeah. John Beck, okay.
Not the art raw musician Beck.
That's
So
yes.
I have a question about this distributive law construction. Let's say
Yes.
you have one, so that P circle Q inherits this operad structure.
Yeah.
So algebras over P circle Q do have an underlying P algebra and Q algebra?
Yes.
Just taking the units?
They do. Yeah, exactly. Taking the units, that's what will give you that thing.
Okay.
And then the relation between the operation is expressed by the distributive law itself, the lambda
So
here.
is that related to the Bortman-Pope tensor product? It sounds like the Bortman-Pope tensor product would be some kind of extreme example, right? Because in a
Yes, so
tensor Q algebra, you're saying that there's a P algebra structure, a Q algebra
So,
structure, and the P operations are Q algebra.
but there's a difference between the, because the Boardman-Vogt is in fact related to coproduct of operads, which means that technically you don't have to order the way that you act with P and Q, but Boardman-Vogt had this interchange law, which looks a lot like the interchange law for level algebra that I wrote before, but they're interchange law between two operations, one from P and one from Q. So in the end, you can reorder everything. So it gives you this impression, but I'm not sure there's actually a connection between the two, or I don't know how to write it as at least. The relation would be something like the distributive law gives you the interchange law for all of Q and P. I'm not sure that that makes sense.
So the circle there is that symmetric product.
That's the composition product of operad. That's the normal one. All right, so let me give you a couple of examples before I stop. First, if you have an operad P, you can consider a new operad, which I call der P, whose algebras are P-algebras with an internal derivation that if you try to write what a derivation means for a P-algebra, it's the same thing that you would think for derivation on associative algebra or commutative algebra or Lie algebras. Now, since I have a new operad, I can look at the divided power algebra structure. And it turns out that this operad der P is given as a distributive law, a very easy one between P and another operad that is concentrated in RET1. So I can use my result from the previous slide to compare those two structures, the divided power der P algebra and the divided power P algebras, and it gives me that divided power der P algebras are divided power P algebras endowed with a sort of derivation that satisfies that extra condition with respect to those divided power operation beta. And this is a good candidate to what we can define as being divided derivations. Now the question is, let's put it to the test. Let's take, for example, the operad of commutative associative algebra. What is the relation that we find on this derivation? Well, we find exactly a relation that Cartan had noticed on some of the examples that he had in mind, but that was recently rediscovered by Ioannis Doukas in his work on Beck modules over divided power algebras. And that also links to another kind of formula that was in an article of Keir and Pritchard on divided power formal series. If I take the operad of Lie algebras, the notion of divided derivation that I find corresponds to a notion of derivation for restricted Lie algebra, which was already in the historical paper of Nathan Jacobson, where he kind of defined restricted Lie algebra back in the 40s. So it means that I'm recovering things that, in fact, I should have expected from the beginning. Now, my time is almost done, so I'm going to quickly show you my last slide. The thing is, this result relating divided power of distributive law with the divided power of both operad is complex enough that even with easy distributive laws, you can sometimes get stuck and not be able to actually characterize your divided powers. For example, the classical example of a distributive law is given by the operad of Poisson algebra. So if you remember what a Poisson algebra is, it's a commutative algebra and the Lie algebras, and there's a certain distributivity relation between the bracket and the multiplication. So the bracket of a multiplication has to be given as a sum of products of brackets. That's a distributive law. And in the original paper of Fraisse in characteristic 2, he showed that a divided Poisson algebra was a Poisson algebra that also had a restricted Lie algebra structure, a classic divided power algebra structure, satisfying those three rules here, which gives you the distributive law between the three. And he has some sort of conjecture of what should happen in general characteristic, but he can't prove it. So I come in with my result and I say, okay, I have an actual expression formula to compute those distributive laws and divided powers. Let's try it. And it turns out that if I try it in characteristic 2, I can prove this in a couple of lines. That's fine. That's good. We've proved that. I knew what I was expecting. I tried to do that for general characteristic and it didn't quite work. So I tried characteristic 3. And it turns out that to prove the result that I have underneath, which is quite close to what Fraisse has with a tiny bit longer relation in the middle, took me 6 pages to prove using rewriting combinatorics, and it's a very, very long procedure. And in fact, it turns out that that proof explodes in length if you bump up the characteristic. So I don't even have any hope to solve characteristic 5. There is some hope that maybe I can enter that into a computer and the computer will do that for me. But personally, I don't know how to do that. And I've asked the people who know how to do that and they didn't seem that interested. Although there's kind of a motivation for doing that is that this, what's hard to find here is always this relation B. And those polynomials that appear here, Benoit Fraisse has conjectured that these are some kind of polynomials that appear in the computation of the cohomology of Cn+1 spaces by Ralph Cohen. So it has kind of a deeper application to topology that I'm not sure I completely understand, but it comes from the fact that this operad of Poisson algebra kind of governs those things. All right, that's all I wanted to say for today. So I wanted to thank you for your attention. If you have any question, you can ask them, of course.
Let's thank our speaker. Any questions?
Just
Check for questions online.
yes, so if you are online and you have any question, don't hesitate to write them or raise your hand. Problem is that I'm not sure I can hear them if they speak.
Can you hear me?
Yeah.
Okay. I do have a question, but there's a couple of things. One of the classical results that your work reminds me of early on, at least, was this characterization of fixed point spaces. So if you act on a multivariate polynomial ring by Sn or some Coxeter group, there's an important theorem that the fixed point space is a polynomial ring over different variables.
Yes, I think I see what you're talking about. So that's.
I just wondered if that was used at all in
But there's a funny tenuous connection that I can see, that this fixed point, like this fixed point algebra within the polynomial algebra, there's sometimes related to Chern classes, right?
Yes.
And those algebras are used to prove a certain version of the Poincaré-Birkhovitz theorem, which in positive characteristic does include divided powers. So it means that there's a divided power Poincaré-Birkhovitz theorem. And I'm pretty sure that the kind of algebras that you're talking about, they play a central role in giving like generators of a certain kind of algebra that you're looking for. But I don't remember exactly the details of it.
Yeah, yeah, okay. Yeah, it just reminded me of that. It might be useful for you. Yeah.
I think I remember what article talked about that, but I haven't read it in a few years now. So I don't remember what was the connection exactly.
Okay. And you had other, you sort of left open the odd characteristic cases of your divided power algebras. Is that an open problem?
So not really, because as you see, like for example, for Poisson algebra, I do have a characteristic 3 that works. For commutative algebras, we have all the odd characteristic for Lie algebras as well. So it's just that for certain kinds of algebra, such as, for example, the level algebra case, every time the characteristic is odd, the characterization, I can give it to you, but it's not compact. This one is really a level algebra plus one operation that satisfies 3 relations, and that's all. Whereas in odd characteristic, you have an infinite number of operations and an infinite number of relations.
Okay, thank you.
I kind of have a hope that if I look, for example, for the characterization of divided powers over an operand who is generated by one ternary operation and that satisfies suitable associativity and commutativity relation, maybe I should be able to find something quite easy in at least in characteristic 3 and maybe in other characteristic. But as I said, the presentation of an operand doesn't guarantee you the presentation of the divided powers. So it's not that clear that it works.
Yeah, okay.
Questions? What's thanks, Sacha, again, for a beautiful talk.
Thank you.
Thanks for all for your participation. And thank you to our online participants. Take care.